All right, so I think I'm recording. Let's take a look at this problem. We've got two functions, f and g, and in parts a, b, and c, they ask us to build a new function. And they're asking us to do that through multiplication, and in b and c through division. And then in part d, it's asking us to find the domain of each one of these new functions that we just built. So let's jump in and take a look at part a. The name of this function, fg, of x is a nice name because it tells us how to construct this function, and that means to take the function f and multiply it by the function g. So what we get here is that f of x is this fraction, this ratio, and since I have a fraction and I'm multiplying it, I'm going to write this square root of x minus 6 as a fraction by just saying divided by 1. And you can always do that. All right, so I have a common factor in the numerator and denominator. And so this reduces to just the number 1. And here's where you have to be careful. Because if they had started the problem here and said, find the domain of this function, you would say, well, the domain is all real numbers. But if you're aware of how it was built, f and g, you're ignoring that given information. And what we know about f and g is that they didn't have a domain of all real numbers. They were restricted, and that restriction carries through. If we want to find the domain of this new function, we have to consider how it was built and take the domain of f and intersect it with the domain of g. So the first thing we want to do is come over and find the domain of f. So we look at the denominator here, and we see two things. We see that there's a variable in the denominator, and we see that there's a radical. So two things have to be true at the same time. We can't allow x to be 6 because 6 minus 6 is 0. And we need x minus 6 to be greater than or equal to 0 because we can't take the square root of a negative number. So this is x greater than or equal to 6. But these two things together tell us that the domain of f, you have to exclude 6, and that is 6 to infinity. So let's make this a bit smaller. Here's the domain of f. Well, let's take a look and see if we can't figure out what the domain of g is. With the domain of g, we don't have a variable in a denominator to worry about. All we have to worry about is that we want this x minus 6 to be greater than or equal to 0, because it's okay to take the square root of 0. It was just not okay to divide by it. So in the domain for g is greater than or equal to 6. So the domain for g is greater than or equal to 6. So when you have two or more sets that you're trying to intersect together, I suggest that you draw it on a real number line so that you can kind of get a better visual as to what's going on. So let's come over here and draw a number line that represents the domain of f. A number line here represents the domain of g. For the domain of f, we exclude the number 6 and include numbers that are greater than 6. So here's how we would sketch the domain of f. For the domain of g, we include 6 and all numbers greater than 6. So to be in the intersection, to be in this domain of this product fg, you have to be in both sets. So 6 is clearly not in both sets, so 6 will not be in the intersection. To the left of 6 is not in this set, so it's not in the intersection. To the right of 6 is in this set, and it's in this other set. Therefore, since it's in both, it's in the intersection. So our domain for part A is from 6 to infinity. And I don't believe that you wouldn't get that answer at all if you just looked at this final product here, because you haven't considered all the information that was given. You haven't considered how it was constructed, and that's very important, that information that was given there. So for part A, here's our answer of what the product is, and in part D, here's the domain of that function, and that's what they wanted. So let's erase this and go on to part B. Now I'm going to keep my domain of F and my domain of G. I don't want to erase that because I'm going to refer to it. All right, so let's shrink that up, however. All right. So let's come over and figure out what this new function, the equation of the formula of it is. So the title, this f over g of x, is a nice title because it tells us to take the function f and divide it by the function g. So the function f is itself a fraction. And the function g. Now, students often do better with a complex fraction. Instead of using this fraction bar as division, to go old school and write that fraction bar as a division symbol, and then this denominator to even make it a fraction by putting it over 1, because that seems to do a very good job of jogging your memory and to recognizing that division is the same thing as multiplying by the reciprocal. That we can change this division to multiplication if we take the reciprocal of this divisor, if we flip this fraction. And this simplifies very easily. You just multiply straight across the numerator. And when you multiply these radicals together, we do have a property of square roots that say if you have a product, then you can write it as a single square root of a times b. Well, so that means that that I have the square root of x minus 6 squared. And now this is me being picky, but the square root of that is the absolute value of x minus 6. Now, because we can figure out what the domain is, we'll be able to drop those absolute values, but not for every problem. So that's why I keep insisting that you should consider it, because there are times when you can't drop it. All right, so let's find the domain of this f over g. The domain of this f over g starts out in the same way of finding the domain of a, and that's to take the domain of f and intersect it with the domain of g. But we have this added restriction that we need values of x. We need to avoid that the denominator is equal to 0. So we've already figured out what this set is. We have already figured out that set was 6 to infinity. And now all we have to do is let's take a look at g and try and determine what values of x cause g to be 0 and throw that out. So I need to come over and solve, let's do it over here. I need to temporarily let g of x equals 0 and solve this equation. So it's easy to see by inspection that x is equal to 6 is a solution to this equation. So we want to throw out 6. we want to have all real numbers excluding the number 6. All right, so let's come over, and I'm actually going to erase this because I want to write some things underneath this number line. So, and I need to make some room to do that. So the set of all x that satisfies g of x not being 0 is all real numbers excluding 6. 6 is the only value that if you evaluate g at 6 that you get 0. Now, to be in the intersection, you have to be in all 3 sets. So it's clear that 6 is not in the intersection because it would have to be 6 would have to be a solid dot in all 3 sets. So we exclude 6. Even though this is shaded to the left here, it's not in all 3 sets. It's not in these 2 sets, so we do not include numbers that are less than 6. But what we do notice is that in all 3 pictures here, in all 3 sets, any value that's greater than 6 is in all 3 of these sets. Therefore, it's in our intersection. And so our answer here is that the domain of f over g is strictly bigger than 6. So being strictly bigger than 6, like 7, 8, 9, hey, x minus 6 is going to be positive anyway, so I can drop this absolute value, and my answer for part B is 1 over x minus 6. I was able to drop the absolute values because of the domain of this f over g was all real numbers strictly greater than 6. All right. Now, I don't want to, there's parts of this I want to keep. I want to keep my domain of f and g, and I also want to keep this time my answer for part B, because if I look and compare my answer for part B against my answer for part C, I see that these are reciprocals of each other, that f over g and g over f. All I have to do, now that I've done the work in B, is to recognize that work and to say, well, if you take g of x and you divide it by f of x, what you're going to get is the reciprocal of this. And the reciprocal of 1 over x minus 6 is just x minus 6. Now, I need to find the domain of that here in part D. So the domain of this, we do it very similar to what we did just here a second ago. We take the domain of f and we intersect it with the domain of g. And that we've already have. That we know to be strictly greater than 6. We need to intersect this with all values of x. We need to avoid this denominator f of x from ever equaling 0. But if we look closely at f of x, does f of x equal 0 even have a solution? Because f of x is 1 over the square root of x minus 6. And I claim there's no way that this fraction would ever reduce to 0, because the way that a fraction reduces to 0 is if the numerator is 0. Since this numerator is constantly 1, there's no way that 1 is ever going to mysteriously change to a 0. So I'm not adding any further restriction here. All numbers, if I want to exclude any values that cause this to be 0, I'm not excluding anything. So to be in all 3 sets, once again, we're getting an answer that is 6 to infinity. So the thing to take away from this is that you can find the domain of these functions that you build by just looking at f and g. And in fact, that's what you should really do, because if you find this new function and you write it in lowest terms, if you reduce it, then you may be losing information that is critical in determining what the domain of this is. So, hey, I hope that helps. I'll talk to you later. Bye.